What if I told you that every time you use Google Maps, play a video game, or watch a robot navigate a warehouse, you're witnessing one of the most elegant algorithms ever created? This is A*, and it's not just another pathfinding algorithm, it's the gold standard. A* finds the shortest path between 2 points, but here's what makes it special. It does this incredibly efficiently by being smart about which paths to explore. While a naive algorithm might check every possible route, A* uses a brilliant trick. It combines what it knows about where it's been with an educated guess about where it's going. Today we're going to understand exactly how A* works, why it's optimal, and why it's been the go-to pathfinding algorithm for over 50 years since its invention in 1968. Let's start with the problem A* solves. Imagine you have a grid representing a map. You're at a starting position and need to reach a goal. Some cells are walkable, others are blocked by obstacles. The question is simple. What's the shortest path from start to goal? Now you might just think, just try all the paths and pick the shortest one. But that's incredibly wasteful. If your grid is 100 by 100 cells, you could have millions of possible paths. We need something smarter. The key insight is this. We don't need to explore paths that are obviously going in the wrong direction. If we're trying to reach a point to the east, why would we spend time exploring paths going west? A* formalizes this intuition into a precise mathematical framework. Here's the heart of A*, and it's beautifully simple. For every cell we consider, we calculate a score called F. This F score is the sum of two components, G and H. The G value is the actual cost to reach the cell from the start. This is something we know exactly because we have already traveled this path. The H value is a heuristic, an estimate of the remaining cost to reach the goal. This is our educated guess. So F equals G plus H gives us an estimate of the total path cost if we go through this cell. The magic happens when we always explore the cell with the lowest F score first. By doing this, we're always working on the most promising path, the one that appears to offer the shortest total journey. This is what makes A* so efficient. The heuristic function H is where A* gets its intelligence, but we can't just use any guess. The heuristic must be admissible, meaning it never overestimates the true cost. Why? Because if we overestimate, we might skip over the actual shortest path thinking it's too expensive. The most common heuristic for grid-based pathfinding is the Manhattan distance, simply the horizontal distance plus the vertical distance to the goal. If diagonal movement is allowed, we use Euclidean distance or the diagonal distance. Here's the beautiful trade-off. A heuristic closer to the true cost makes A* faster by reducing unnecessary exploration, but computing a more accurate heuristic takes more time. The Manhattan distance hits the sweet spot. It's trivial to compute and provides excellent guidance. A* maintains two crucial data structures, the open set and the closed set. The open set contains all the cells we've discovered but haven't fully explored yet. These are our candidates for the next step. The closed set contains cells we've already processed. We don't need to look at these again. The algorithm starts by adding the start cell to the open set, then it loops, take the cell with the lowest F score from the open set, move it to the closed set, and examine all its neighbors. For each neighbor, if it's in the closed set, skip it. We've already found the best path there. If it's not in the open set, add it. If it's in the open set but we've found a better path to it, update its G-score. This process continues until we pull the goal from the open set, at which point we've found the shortest path. Let's trace through A* on a concrete example. We have a 5x5 grid with our start in the top left and goal in the bottom right. There's a wall blocking the direct path. We begin by adding the start to the open set with G equals 0 and H equals the Manhattan distance to the goal. Now we expand the start, we look at its walkable neighbors. For each one, we calculate G as one step from start H as Manhattan distance to goal, and F as their sum. We add them all to the open set. Next iteration, we pick the cell with lowest F. Let's say it's the cell to the right of start. We expand it, calculating scores for its new neighbors. We continue this process and watch how the algorithm efficiently navigates around the wall, always prioritizing the most promising direction. Once a star reaches the goal, we need to actually build the path. During exploration, we maintain a crucial piece of information. For each cell, we recorded which cell we came from, its parent. Starting from the goal, we simply follow these parent pointers back to the start. This gives us the path in reverse order, which we flip to get the final answer. The beauty is that because A star always explores the most promising cells first, when we reach the goal, we're guaranteed this is the shortest path. We don't need to keep searching, we can stop immediately. This is the optimality guarantee of A star, and it comes directly from using an admissible heuristic. You might have heard of Dijkstra's algorithm, another famous pathfinding method. I talked about it in my very first video on this channel, so if you want the full breakdown, go ahead and watch that after this. And here's the key difference. Dijkstra is essentially a star with H always equal to 0. Without the heuristic, Dijkstra expands outward uniformly in all directions, like ripples in a pond. It will find the shortest path, but it explores far more cells than necessary. A star with its heuristic is like a guided missile. It knows roughly where the goal is and prioritizes exploration in that direction. On a large, open grid, Dijkstra might explore thousands of cells while A star explores hundreds to find the same path. The heuristic doesn't change the answer, it just helps us find it faster. This is why A star dominates in practice. Same correctness, dramatically better performance. A star is everywhere once you start looking. In video games, enemy AI uses A star to chase players around obstacles. In robotics, autonomous vehicle plan routes through warehouses and city streets. GPS navigation systems use variants of A star to find driving directions among millions of road segments. Even in artificial intelligence, A star solves puzzles like the 15 puzzle or Rubik's Cube by treating puzzle states as nodes in a graph. The algorithm scales remarkably well. With proper data structures like a priority queue for the open set, A star handles graphs with millions of nodes. It's been optimized and extended in countless ways. Bidirectional A star searches from both ends. Hierarchical A star pre-computes high-level routes. And anytime A star returns progressively better solutions. Let's look at the core implementation. The algorithm initializes OpenSet with start, then loop while OpenSet is not empty. Pop the node with minimum F score. If it's the goal, reconstruct and return the path. Otherwise, add it to closed set and process each neighbor. Calculate tentative G score. Skip if in closed set with better score. Otherwise, update the neighbor's scores and parent, and add to open set if new. That's the entire algorithm. A star represents a perfect marriage of mathematical elegance and practical efficiency. It's optimal, guaranteed to find the shortest path. It's complete. If a path exists, A star will find it, and it's efficient. The heuristic dramatically reduces unnecessary exploration. 50 years after its invention, A star remains the foundation of pathfinding and computer science. Understanding it deeply opens the door to countless applications in games, robotics, and AI. If this was helpful, don't forget to hit the like button and subscribe if you want to see more videos like this. Thank you guys for watching.